Yeah.
I think that's what we're in this.
Right. So it's not like,
Oh, yeah.
like this.
All right.
Okay. Okay.
All right. Continuing with the ANOVA, I want to just kind of go over what the signal to noise ratio was. All right, so here's another way to think about it. We've got our individual groups, and the groups have like a variance associated with their data. All right, so group A, that's the data point. This is what we're looking for normality of. We're looking for normality on those data points. We're looking for normality in these data points. We're looking for normality in these data points. That's what we're looking at for our assumption. And then the way that ANOVA works is it calculates how much variation there is in the groups themselves. That's how much noise we have. All right, and that's our variance. And the way it works is that it assumes when it calculates the variance that the variance is going to be the same for all three. All right, and we know it, but they might not. They could vary. That's why we check the assumption. If you have a very large variance for one group, well, you can't then take the variance of this group and assume that it's fixed across all three groups. They differ. So one of our assumptions, and it makes it easier to calculate by hand, is to say, I'm going to calculate the variance in group A and then assume that that variance is the same across the remaining groups. All right? So this variance within each of these represents our noise component. All right? It was the sum, in here we have the sum of our squared deviates. So quickly just kind of go back to what our variance is, that s squared. That was the sum of our x minus the x bar squared terms divided by our sample size minus 1. What we're doing here is this. That represents our sum of squares, sum of our squared deviates. All right? So if we do the sum of the squared deviates of each of the values and divides it by the number of groups minus 1, that's going to give you basically the variance within the individual groups, more or less. So that part's our noise. Our signal can be thought of as how much variation you have from our individual means to the grand mean. Because what it's going to do is figure out how many data points we have. Let's say we have n equals 5 for each, except for the C. We'll say that's 10. What it's going to do is calculate this squared deviate. So that's the mean of our group A minus our grand mean and square it. And then it's going to multiply it by our sample size. And it's going to do that for each of these. All right, so we can kind of fix the sample size. And that kind of tells us how far away on average our means are relative to the grand mean. And that's our signal. So the farther these points are, the more signal we have in our F statistics saying, hey, these means are not equal. Eventually, these are so large that they swamp out any of the variation that exists within our group, allowing us to detect this difference. Does that help? All right. It's kind of I haven't really found a good way to explain it or to share somebody's explanation, but that's kind of this is what ANOVA is doing. It's looking at the variance within the groups using our sum of squares term, all right? And it's comparing it, the within, to the between, how far away each of our means are to that grand mean. All right? Any questions? I just didn't like how I explained that this morning. Wanted to clarify.
Can I just like apply a real life situation to that?
Okay.
Okay, just so in my head. So you're getting like back length, and you're looking at different species.
Okay.
So the grand mean would be the mean of the entire like data set that you have
Mhm.
And then you're taking, like A, B, and C would be different species. So you might have a larger species that varies completely different, like a smaller species. So you're comparing the means of like one species and then another species, and then another one, and you're seeing the variance between like those three.
It's the variance from our individual data points to the mean. So what's going to change is that X bar.
Okay.
So our variation within our groups, we're going to have a sum of squares for group A, which is all of our A data points minus the mean of group A squared. And then we're going to have a sum of squares of B, which is all of our B data points minus the mean of our B. And we're going to have the same thing for the C. And what we can do is add them up to get our total sum of squares. But when we do it by hand, we take the shortcut and say they're all going to be equal. All right, so you calculate one, then you multiply it, and you get the same value. All right, or actually, you do all of this, and then when you divide by your total sample size, there's total sample size minus k. All right, no. K over k minus 1 is where we get back it to make that assumption that they're all equal. So if they're not equal, then we will change our degrees of freedom. You'll see the output because we have something that will correct for that when we don't have the same sample size. So we're going to have the sum of squares. This is the variation. This is all of the noise. And then to see if there's a difference in groups, instead of doing all of A to the mean of A, then what we're going to be doing is the mean of A, or I should say, all of our A values minus the grand mean. So all of our points back to this mean. And when you do that, it's basically comes out to be the mean minus the mean of group A minus the grand mean squared times however many data points we have here. It's just the way the math works out. So then this one is all of your B points minus your grand mean squared, and then times your data points. And all of these points would be all of your C's minus the grand mean squared, and so forth. So what's kind of changing is what this X bar is in reference to. Is the X bar in reference to our individual groups, or is it in reference to our grand mean? If it's in reference to the grand mean, then the more we're different, the larger these terms become.
So that X bar A, that could change, or
That's the group mean of A. So our aggregate function for our plant growth, these X bar A, that would be your control mean. This would be your treatment mean, treatment 1 mean, that would be your treatment 2 mean.
Okay.
And then, since we're on the plant growth, let's open up our studio. Plant growth, where's my cursor? It is. There it is. These are the mean, right there. Here's our means. That's what we would do our within group variation. This is our noise part. It's telling us how much variation we actually have. And then if we wanted the grand mean, it would be the mean of plant growth weight. 5.07, and that's what we subtract for each of ours. So we can kind of go through and do this. So, if we did it by hand and we wanted to know our variation, our sum of squares, what we would do is take each of our x's, plant growth weight minus the grand mean. 14.25843. So we took each of our data points, we subtracted the grand mean, squared it, right? And then I took the sum of that, and that's basically the sum of squares. Sum of the squared deviates. Now we can divide by our degrees of freedom in this case to get our mean squared term. It's we're kind of going. We're kind of based on the theory. We're not really going to do this by hand because R will do all of this for us. So I think what we'll do is we can come back to this, and I can show you kind of where all of these terms came from, if that helps you better understand how it's doing. All right. So we're on our normality assumption. I put in the request to update. Put in the request right after class. I think it was completely unlikely that they would get it done before our 2 p.m. No big surprise. I make the request. It has to be approved by somebody in IT. So I'm sure, I know it's going to get approved. I should have probably, I think version 4 came out after the classes started. I think it came out in September. So I think we were on the most recent version. Then when version 4 came out, that's when I noticed CAR was also updated. And I thought, oh, that is great. So if you have a new computer, or if you have your own computer and you have the new version of R, what you can do is this code, QQ plot weight as a function of group, and that will, which one? R screen. Oh, sorry. There. Sorry, yeah, I was typing. Yeah, so we would use this code to get all of our QQ plots all at once. All right? At least 2 of you had your own computers. Did you try it? It worked for you? All right. But on mine, and the computers here on campus, they haven't been updated, so we're going to get the error message. Is that going to hurt us? No, not really. Because I'm going to show you an alternative method of getting our individual QQ plots. All right. So we're going to use the alternative method using what I call the subset function. And that's actually what it is. It's a subset function. Let me go over here and just kind of describe what it's doing. So a subset is going to take a subset of your data set. And it's going to take the subset based on some requirement that you make, some specification that you make. All right? So what we do is we issue subset, and then we tell it the data frame that we're going to take the subset of. And then we specify our condition. Now our condition can be a single condition, or we can write some sort of complex logical statement. We can use and, we can use or, and so forth. The graduate class will kind of get into that complex subsets. All right? But what we're going to do is we're going to take a subset of our data frame, whatever data we're taking it of, and then we're going to select on a specific variable. All right? We're going to select on a variable, and we're going to say on this variable, we want to select out all of the items that are equal to a specific value. All right? And then that subset's actually going to give us a data frame, but only include those items that correspond to our condition that we set. So for example, run this. Subset Planck growth comma group equals, double equal sign, CTRL. And CTRL has to be in quotations. All right? you run it? Did you see what you get? All right. So here is my markdown. I added in some additional comments. Just again, just kind of transferring what I had on the slide into my markdown document, so I have it. All right, so the subset data comma condition, where we specify the condition that we're selecting on. For this QQ plot, our condition will be a variable and the level of interest. All right, we're interested in pulling out a single level of interest. So for us, we're going to use the plant growth data set. And the plant growth data set has two variables. It has the weight variable, and it has a variable called group. All right? So that's why I put group here. It's not I'm taking a grouping variable. That is the name of the variable that we're selecting. The double equal sign sets up the logical. If you just did one equal sign, then R would try to say group is equal to a single value, and then it'll complain. But if we have a double equal sign, that tells R, hey, I'm looking for a logical situation. All right? And the group that we want is CTRL. So when I run this, R returns a data frame. All right? It returns a data frame that has the same columns, same variables, as the original, has the weight and the group variable. But you'll notice that we only have 10 items. The 10 items that were returned were only the ones that corresponded to the CTRL level, the control level. All right? So once we have the subset, then what we can do is pass it on to our QQ plot. Right? So the subset returns a data frame. As with any data frame, we can utilize the $ to reference an item inside the data frame. So we'll reference a variable in the new subsetted data frame using the $ notation. And we'll then pass it to our QQ plot function. So we're going to do QQ plot. What are we doing a QQ plot of? Well, we're going to have a data frame. The data frame that we're going to use is our subset data frame. This is only the CTRL items, but I don't want a QQ plot of the entire data set. I only want the QQ plot of the weight variable. And now I would run it. And if I run it, I know I should fail because car is not loaded. So now car is loaded, and when I run it, I get a QQ plot of weight, but only for the CTRL group. All right. Now, we want to do, this is checking normality just of the control group. We also have to check normality of the treatment 1 and the treatment 2 groups. So using the same subset notation and passing all of this onto QQ plot, take a few minutes to try to write the code, update the code, so that we can get a QQ plot of our treatment 1 and our treatment 2. And we're going to use these subsets because sometimes when we do our post hoc tests by hand, a series of pairwise t-tests, we have to subset out the two groups that we're comparing.
You have to subset each one of those groups out or plot other groups?
No, you can copy and paste that code and just update it. So let move that. Move this far off to the side. Did you hit it?
Where do we go to look at plant growth? Can we just look at that like a table form?
Yeah, you could.
How? It's not in my environment. I don't know.
So down in the console, type in plant growth. Or what you can try to do is do summary of plant growth. See what it gives you. But why were you curious?
Because sometimes it helps to look at the table and see if your data makes sense.
So one of the things that as we do this, it's what did I call my levels? Right? We use the aggregate function. We can look at those. But if I'm doing a series of QQ plots, I like to write all the codes together all at once, and I need to know what my names are, right? So I use levels. Levels tells us the levels of a grouping variable. So levels of plant growth $group here tells me that I have 3 different levels: CTRL, TRT1, and TRT2. So once I know those, I'm going to go ahead and do a series of these QQ plots. I'm going to probably do one first, just to make sure it works. And then I copy and paste it however many times I need it. And then I just replace each of those spots with the levels that R returns to me. Summary would do the same thing, usually. I do think there's an upper limit on how many levels it gives. It'll give maybe the first 5 levels or so, and then it'll say other for all the rest, which doesn't really help us if we have a lot of levels. But this gives us a way to quickly view how many levels we have in that variable. Now, what's interesting is if you do your subset and do levels on that, it'll still return 3 different levels, even though your data set doesn't have all of them, because when R reads this in as a data frame, it says, okay, group variable is a factor. These are the levels that I'm looking for. All right? So, did you run it? Did you get it working? I get all 3 of these. And we only have a sample size of 10. So there's really, Shapiro-Wilkes is going to be real questionable. Actually, it wouldn't pick up any non-normality. And just looking at all of these, the only one that's maybe questionable is this, treatment 1. How do I know it's treatment 1? Check the axis. It says TRT1. All right, it's a subset plant growth TRT1. And it's really just those 2 points at the end. 2 out of 10, it's 20%, but we still only had 10 data points. And when you take a look at the other 2 groups, they all look pretty good. They all look pretty good. So what do you say here? Normal, non-normal? I think we're normally distributed. All right. So we're going to use this, and just again, I'm going to emphasize this here. That's why I said variable equals some value. This is the variable name in your data set. It's not just group. You don't use group all the time. That variable name changes based on our data set. So I think for our fish length data set that will come up, I think it's lake might be that level. We'll see. All right, so normality. Remember the assumption is normality within each group, and that's why we're doing it. We have to check the normality within each group. And we did all of these. Don't trust the Shapiro-Wilks, too small. So I say we're normally distributed. And then we go on to our equal variance assumption. Remember, that's homoscedasticity is what we're checking. Our options, Brown-Forsythe test or the Fligner-Killeen test. And which one we choose is based on our decision for the normality assumption. If we're normal, then we're going to run the Brown-Forsythe test. Why? Because this test assumes symmetry around the mean or the median. I'm going to say the median because this test is equivalent to the Levine's test. The difference is the Levine's test tests against the mean. So we need symmetry around the mean. Brown-Forsythe tests for symmetry around the median. And you'll see the code that produces it. All right? Brown-Forsythe is definitely preferred over the Levine's test. And that's why we're going to introduce it. Fligner-Killeen test doesn't make that assumption of the symmetry. It's functionally equivalent to Brown-Forsythe test. However, it's non-parametric, so it's going to utilize ranks and see if the ranks are basically equal. If you have the same level of ranks around each of your medians. So here's how we do a Brown-Forsythe test, and a Levine test, and a Fligner-Killeen test. All three of them. All right. So Levine's test is Levine test. Note your capitalization of the T. All right. In order to run the Levine test, we're going to use our formula. So y is a function of x. In this case, we're going to use our weight as a function of group. And the center that we're testing around is the mean for the Levine test. Now this assumes normality, and we're testing around the mean. I don't really like it because it's not as robust to these slight variations of normality. Because of that, I prefer to run the Brown-Forsythe test. Brown-Forsythe test, same exact function, Levine test, but we change our center to median. So the formulas are basically the same, it just depends on where they're testing our variances from. Are we testing around the mean, or are we testing around the median? Most people suggest doing the Brown-Forsythe test because it is more robust to these slight variations of normality, which ANOVA is really good against. All right. If we choose, and both of these are in the CAR package, so you already have the CAR package loaded for the QQ plots. Nothing else we have to do to get access to these tests. Fligner-Killeen test is going to be our second choice. So if we're non-normal, and we know that we're non-normal, then I say go ahead and do the Fligner-Killeen test. If you're questionable, I'd probably also say go ahead and run this test. Fligner test is built in, Fligner.test. It's built into the base package, so we don't have to add anything else. And we're going to write it the same way. We're going to write it as a formula where we have our dependent variable as a function of our independent variables. Since we're referencing the variable names, we give it the data frame, and then R will see the output. Now, this test is non-parametric, so it's not as powerful as the Brown-Forsythe test, which means that the Fligner-Killeen test, we run it because we were questioning whether or not our data was normally distributed, and we get a p-value that's close to 0.05, say 0.06, 0.07, 0.08. There's a possibility that we violated the equal variance assumption. We just didn't have enough power to detect that difference. There's kind of a warning with that. All right, so we're going to run our Brown-Forsythe test, and we're going to run our Fligner-Killeen test. So these are the two ways to run it on our plant growth data set. All right, I have it in here. So I'm going to go to R. And I'm going to do my write-up or conclusion right now is that the data appear to be normally distributed within each group. Our next task is to check the equal variances assumption. All right. So since it's normally distributed, we'll run the Brown-Forsythe test. This function is in the car package. Just to kind of emphasize, if you were doing this and you got to it, say, oh, I'm getting errors, it's not found, why not? It's in the car package. So, Levine test. You see two options, they're both the same. This Levine.test is being phased out. I don't even know if it's available in version 4. So, we're using Levine test, no space, but with a capital T. We're testing weight across our groups. And the data that we're working with is plant growth. All right, so Levine test, weight is a function of group. So we are testing equal variances of our weights across the 3 different groups that we have. We're going to run it, and we're going to get our output. And you'll see the default is center equals median. So it really saves us time and keystrokes, which is nice. I mean, I'd say if this is the default option in R, it's probably what's recommended, right? Safe to assume that. So this is Levine's test of homogeneity of variance. That's what it says. Center equals median. That tells us, center equals median, that tells us that we're running Brown-Forsythe. All right? This isn't going to say Brown-Forsythe test. It actually tells us that in the help file, that center equals median is running the Brown-Forsythe test. Here's our stats output. Now, in this output, it doesn't tell us our conclusion. Like the t-test says this is the alternative hypothesis and so forth. For us, our null hypothesis of this Brown-Forsythe test is that our variances are equal. Our alternate is that at least one of the variances is different from the rest. What do you say? Do we have equal variances? What do you say? Let's get our null and alternate hypothesis in there for this Brown-Forsythe test. And I know we'll go over it again. Are the variances equal?
That have to be exactly one for it to be
What's that?
equal. Does that have to be exactly one for it to be
No, because you've got,
equal?
yeah, stochasticity. If we repeat it, we're going to get slightly different numbers, right? That's why we have a test statistic. That's why we compare our test statistic to the hypothetical test null distribution, right? To get an area under a curve. So what's our p-value? What's a definition of our p-value? Let's start there. I might just have that as a short answer response. Give you like 5 points worth. Make sure you drive that home in your head that you can actually define it word for word. It's a p-value. Look it up. Look it up. It's in our notes. Where was it? Did you get it? Find it?
Isn't it just the probability of getting that data from random chance? Yeah, they want to due to random chance, and it's the area under the curve.
Yeah, p-value. Probability of obtaining data as extreme or more extreme than our observed value if our null hypothesis is true. So our null hypothesis in this case for a Brown-Forsythe test is that our variances are equal. And if our variances are equal, then yeah, our F ratio is probably going to be 1. So what we're looking for is, we have a test statistic. How likely are we to get this or something more if our variances actually were equal? That's what this is. That's what this is saying. What's the probability of getting a value greater than F than our test statistic under the assumption that our null hypothesis is true? So this 0.34 is our p-value. So if that's our p-value, what's our conclusion? What's that?
That you reject the null hypothesis. Variance are.
No, it's that didn't say. Right?
Oh, yeah.
Variances are equal. P-value is greater than 0.05. So we fail to reject our null hypothesis and thus conclude that variances are equal or data are homoscedastic. So we ran a Brown-Forsythe test. Our F is in our output, 1.12. Remember our rounding, we just go to 2 decimal places for our test statistics. Now we have 2 degrees of freedom. We have a group. Number of groups minus 1. That's our first degree of freedom. And then we have 27. We had a total of 30 rows, so n equals 30 minus the number of groups, 3, which gives us 27. That's going to give us the same degrees of freedom as our analysis of variance. So if I was writing it like this, writing it out in a markdown document, I would say df1 is 2, comma, df2 is 27. And then our p-value, 0.32. I think I might just do this. All right. So our conclusion interpretation, variances are equal. What test was run? Brown-Forsythe. How do I know that? Because we set the center equals median, or that was the default. Our test statistic F was reported. Both degrees of freedom were reported because our F depends on those 2. And then we report our p-value. If we wanted to write it or do it in the subscript, we can. So we would report Brown-Forsythe. And then I'm going to do this. And I'll tell you what this means. So if we were in a Word document where we can put up a subscript easily, this is probably how I would do it. So in R, in this markdown language, usually I can use this underscore to represent a subscript. There's some other ways to do it. I think sub HTML markers can also do it. But in the subscript, I would write 2,27. So it would appear as an F, capital F, and then on subscript, it would be 2,27. This is preferable if you're reporting it in a paper, because it's fewer characters in line, right? Because in here, we're going to have to do df1 equals 2, comma, df2 equals 27, whereas here, it's all in subscript. We basically 4 characters here versus 5, 6, 7 for the space, plus another 6. That's how many characters. So that's how we can report it, in a Word document. All right, so that's our Brown foresight test, and it looks good. But let's say you questioned whether or not that second one was normally distributed, and you didn't want to make a mistake. Right? You didn't want to commit a type 1 error all because it was non-normal, or just any error in that sense. We're going to use Fligner-Killeen test when we question our normality assumption. So our null hypotheses are the same. Variances are equal. Our alternate hypotheses is that at least one variance differs. All right? And this function is just Fligner.test, and we do it the same way. So we're doing weight as a function of group, where our data is plant growth. And we get an output that tells us everything that we need. Fligner-Killeen test of homogeneity of variances. We tested equal variance. The test that we ran was the Fligner-Killeen test. The data that we did, weight by group. So we tested the variances of weight across the different groups, across the levels of the group variable. Now, the test statistic in this case is a chi-squared test statistic. All right. So chi-square test statistic, we're testing that test statistic at chi-square is being compared to the chi-square distribution, and that distribution is defined by our degrees of freedom. All right, and then a p-value, and this one actually says here's the p-value. All right, so what's our conclusion? Data appear to be homoscedastic. Variances are equal. All right. This time we ran a Fligner-Killeen. All right. Our chi-squared, and this is where it's better. If we were in Word, that's for sure. So chi-squared equals 2.35. Our degrees of freedom, 2. And our p-value, 0.31. Just remember our rounding. Test statistics go to 2. Our p-value gets rounded based on the value of the p-value. So we're above 0.05, we just go to 2 decimal places for that. So we have 2 different tests. Do we run both of them? No. You don't run both and pick which one you like best. That's not what we do. All right. The decision on what test to run between Brown foresight and Fligner-Killeen comes down to your conclusion, your interpretation of the normality assumption. So if everything looks good, that it's normally distributed, run Brown Forsythe. It has more power to detect unequal variances. If you have any suspicion that the data might be non-normal, I probably run Fligner-Killeen. Caution, if the p-value for Fligner-Killeen and normally about 0.08, 0.08. There. So if the p-value for Fligner-Killeen is between about 0.05 and 0.08, so it's not significant, we wouldn't reject our null hypothesis yet. Just be aware that we might not have enough power to detect that unequal variances. And we should kind of look at other things to say, okay, well, if we don't have enough power and we're close, are there alternative methods that we can use that doesn't make this equal variance assumption? And there are. So you can kind of say, see what happens when we violate assumption, kind of go from there. All right, questions? Note, and this is why I have it here, and this is why it's in red on this slide, that Fligner-Killeen is a non-parametric test. All right? So it doesn't have as much power as Brown Forsythe. If Fligner-Killeen finds significance, gives a p-value that's less than 0.05, then Brown Forsythe will always give a p-value less than 0.05. All right? That assumes that we're normally distributed. If we're not normally distributed, you can't trust this. You can't trust this because we could be getting a bad Brown Forsythe measure. But if we're normally distributed and we run a Fligner-Killeen test and p-value is less than 0.05, you'll always get a less than 0.05 for Brown Forsythe. That's just the way the power works. All right, so we have all of our assumptions, right? Everything's good. Let's run an ANOVA. How do we do it in R? There's actually a couple ways. Some packages have an ANOVA formula or function that will do it for you. All right. The base function allows us to run an ANOVA. It's called a one-way dot test. We'll use that when we violate the equal variance assumption, but we're normally distributed. So you'll see that. What I'm going to introduce you to is this other method, which is for us to first create a linear model using the LM function. And then once we create our linear model, we'll obtain an ANOVA table. All right, why do we do this? I do this because as we add variables, as we add independent grouping variables, this is what we're going to use. So all of you taking the grad stats, which is a lot, we're going to use this. And then the ANOVA table doesn't just run the ANOVA, it partitions the variance into the different factors, into the different variables of interest. So we can see, does the group variable have an effect? Does size variable have an effect? All right, on all that stuff. So what we're going to do is create a linear model first, and we're going to save it. We're going to save it as a new object. And then once we have the object, we'll issue our ANOVA command on that object, on that model, and we'll get an ANOVA table. Now, the ANOVA tables, we can run an ANOVA with all lowercase. This is built into R. Or what I'm going to tell you is to use a capital A for our ANOVA function, because then that references the ANOVA table in the car package. All right, so here's how we can do it in plant growth. So in your R markdown, go ahead and do these back to back. So what I did is I called it model, which is probably a bad term. I probably should have called it mod 1 for model 1. And that's actually what I'm going to do. So this was the code. We're going to get the same thing. let's go back to our markdown. All right, so I'm going to call it mod 1 just for model 1, and then I'm going to create a linear model. What's our linear model? We are predicting weight as a function of group. That's what we're doing. And I wrote it as a formula so that I don't have to use all of my dollar signs. I say, here's the variables, here's my data frame. I'm going to create that linear model. All right. And then, I think I looked at something. Check this out. There it is. All right, so we made our ANOVA table. I'm sorry, come on, where did our markdown go? I don't know why it got hidden. All right, so I made my model, and what I'm just going to do here is look at our summary. So I want to see what the model actually is doing. And this becomes more important as we add more variables. But what the output does is it tells us what we ran. We made a linear model. All right? Linear model is just like the add trend line option in Excel. That's what it did. Is a regression model. Likelihood methods, residuals, coefficients, scroll down, model fit information. All right. So what are all of these things? Residuals is a measure of if we met our assumptions. So for this case, with a single variable, we don't necessarily have to worry about looking at our residuals because we can look at our QQ plots pretty easily. So the QQ plots for each of our groups. We can run Fligner-Kleene or Brown-Forsythe pretty easily. But as the models become bigger and bigger and bigger, then we have to rely on the residuals. Now the residuals, if we meet all of our assumptions, the residuals of our model should be normally distributed. What are the residuals? Well, I told you that this is equivalent to the add trend line option in Excel. All right? So let's say we've got a data point or a data set like that. We made a graph. We've got our individual data points around the line, and our best fit line gives us an equation like that. The residuals is how far we are, each point is, away from our line. If all of our assumptions are met, then the collection of all of our residuals should be normally distributed. Next up, the coefficients. The coefficients actually tells us the equation of this line. All right? For us, we have a group with 3 levels. We have treatment 1, treatment 2, and then our controls, not here. Well, where is our control? Where is our control? Any guesses? What's this value? 5.0320. That's our intercept. I'm going to scroll right up here. .032. That third level is in our intercept. So what this summary is telling us is that the control has an average of 5.032. Treatment 1 is 0.371 units below our intercept. So our mean of treatment 1 is 0.47. Is that right? Someone can scroll back. Group 2 is 0.494 units above our intercept. So it's just kind of giving us an idea of the effect of each of our groups relative to our intercept. Now, are we going to worry about these? No, we're not. We're not. I'm just kind of showing you what this summary is giving us. What we're most interested is in this area down here. All right, so the residual standard error, we're not really going to use that. All right, you'll see this again. The multiple r squared and the adjusted r squared. These are important. And actually, you can just go for the adjusted. This adjusted r squared tells us the proportion of variance in our data set that is explained by our grouping variable. So how much of that weight is explained by group? The r squared, 0.2096. 21% of all of the variation in weight is explained by our groups, by our control treatment 1 and treatment 2. All right? That's informative. That gives us something to write in a paper, to present during a presentation. But most importantly is this part. The F statistic, 4.846 on 2 and 27 degrees of freedom with a p-value of 0.01591. This F statistic in the summary says, does our model, weight as a function of group, so including group in this model, does this do better than just looking at a grand mean as an average? Now, that's a long way to look at it, but I know in graduate level stats, we kind of look at this as a measure of should we include group in the model or not? And this clearly says it is. But for us, we're interested in that ANOVA table because that's what we're going to do. That's what we're going to use. So here's our ANOVA table using the ANOVA function from the CAR package. My model was mod 1, so I'm just going to do ANOVA mod 1. And I've got my table. Now this tells me everything that this already gave me because the summary, the linear model, was a simple one dependent variable, one categorical independent variable. Our group, sum of squares is 3.7663, 2 degrees of freedom. The F value, 4.8461. That's the same F statistic listed in the summary. Degrees of freedom, 2 and 27, 2 and 27. P-value, 0.01591, same p-value that's reported. Did group have an effect on our weight? Yes, it did. That was our biological question. Did group have an effect on weight? The other side of the question was, were the mean weights equal across the groups? Yes or no? No, they weren't equal. So, our write-up then, our means differed between the treatment groups. We ran an ANOVA. Our F, do this, 2.27. F statistic is 4.85, so rounded, and our p-value is 0.02. So our ANOVA, our null hypothesis is that the means are equal. Our alternate is that it's not. We created our linear model. Once we have our linear model, we view our ANOVA table, and this tells us everything that we need. probabilities. All right, so we're almost done. We did our ANOVA. We know there's a difference. So the next step then is to figure out which means are different from the rest. It could be that all means are different, or it could just mean that one mean is different from the other two. We don't know. All right. So let's start it up just as an overall write-up to this point. All right. So our overall write-up to this point kind of lays out what we want to do. So we tested the effect of 3 treatment groups on the weight of plants. I don't know what plants, you can look up plant growth help file to see what they did. All right? On the weight of plants. The data were normally distributed based on our quantile plots. All right, so we ran a quantile plots, we looked at them, and we know that they're normally distributed. And the data are homoscedastic. All right, we ran our Brown-Forsythe test. And for that, I'm going to scroll up to get my numbers. Brown-Forsythe. Oops. 1 too many. And what I'll do is I'll use these curly braces to just to kind of represent that I did them as, let's say, a subscript. I think that's going to work for us. All right. And ANOVA suggests that the means are not equal. And now I'm going to report the output of the means, or the output of our ANOVA test. But we're not quite done. So up to this point, we've got everything that we're describing what we did. We laid out the question, all right? We laid out the check of all of our assumptions, quantile plots, and the Brown-Forsythe test. And then we gave the outcome of our ANOVA test. What's going to be next? Our next step is a post hoc test. Figure out which groups are different. All right? And what we'll do is we'll do that on Wednesday. Any questions? Yes? No? No? So I did kind of go over this. And here is our aggregate function. Again, we had all of those numbers just kind of demonstrating how the coefficients can be used. For us, it's not so much because we stop at ANOVA. After we do the ANOVA and figure out what to do when we violate assumptions, we'll move on to chi-square tests and stuff. But for those graduate students, we will come back to this idea because as we add, let's say, a continuous independent variable, like a covariate, that tells us the relationship. We have to look at these to know the relationship. And we also look at the summary table to give us an idea of what terms can possibly be dropped from our models to try to simplify them. All right, I give you more of this stuff, so lack of fit. We'll come back to this coefficient of determination, this R squared, in a bit, and then the F statistic, that is the same one that we get from our ANOVA. And this was the lowercase ANOVA, but it tells us the same information. I say, especially for the graduate students, get into the habit of using the capital A. Get into the habit of using capital A. All right, so everything up to this test, and this is where we're going on Wednesday. All right? All right. Let's call it a day. Let your brain rest. Some of your brains rest.